I know we're still gathering, and I expect that we're going to fill the place up here, but we've got a precious few moments of Dr. Mather's time here. And let's see, I want to do a short introduction. One is just to let everyone know we intend to continue with as a speaker series that if you had seen Dr. Heidi Hamill a few months ago, you can get a chance to see Dr. Mather as a part of the Webb Telescope program. You know, we're on track to launch in October 2018, and we want the entire campus, the company, really the entire public. We've been out there and you know, things like South by Southwest engage with us on the journey, not just after we launch and collect science data, but for you to know, as a part of Northrop Grumman, what this mission is going to do, you know, how important it is, and really to have such an engaging speaker here is awesome. We're actually hosting this week something called the Science Working Group, so there are scientists here in the conference room right next door from around the world. So many countries that are represented, and they get together on a periodic basis to talk about the science of Webb. I had a chance to talk to them about the progress that we're making here, and we had a chance to give them a tour of what's going on in our facilities. So it was a great opportunity for Northrop Grumman to shine. And what they're walking away from, right after I was done talking at the break, they came up to me and was like, wow, now we can actually not just say we know things are getting done on Webb, but we can say we've seen it. We went in a high bay, we saw a template layer, we saw some of the structure, you know, we saw these things. And when they go back to their countries or to their representatives, you know, they get to talk about the progress being made. But I want to get off the stage real quickly. If you don't know who I am the program manager, Scott Willoughby of the James Webb Space Telescope. I've got the greatest job in the company. I tell Wes Bush that on a quarterly basis. And Dr. Mather is the project scientist for NASA. He works for Goddard Space Flight Center as our prime contractor through NASA in Greenbelt, Maryland. He is the lead project scientist as a part of, you know, NASA's team. Again, there's many scientists from both, you know, NASA and like we said, across. This is a worldwide program. European Space Agency, Canadian Space Agency, all contribute to the success of this program. But I like to talk more than I like to read, but I don't want to mess this up. So. Dr. Mather is a senior astrophysicist in the Observational Cosmology Laboratory at NASA's Goddard Space Flight Center. He also serves as a senior project scientist for the Webb, leading the science team and representing the scientific interests in the project management. He attends our PMRs and also other things. So we have a very close coupling with the users of the system, more so than anything else that I've ever worked on before. So he's also a Nobel Laureate, and he'll tell you more about what's going on. So warm round of applause for Dr. John Mather.
Well, I'm delighted to be here because I have a chance to tell you the entire history of the universe and why what we're doing here is so important to that. So I guess the chart gives away my punchline here. But thank you very much for coming to hear this story, and I wanted to have some opportunity to tell you why this is so important, what we're all doing together. So back in 1776, we got our charter. This is a piece of the Declaration of Independence, and Thomas Jefferson wrote these words. He wrote about the laws of nature and of nature's God right at the beginning, and then he said, we hold these truths to be self-evident, that all men are created equal, that they are endowed by their Creator with certain unalienable rights, that among these are life, liberty, and the pursuit of happiness. Well, he was really interested in science. He knew how to use a telescope to get his longitude by watching the satellites of Jupiter, and he would be amazed to see what we have all accomplished, and I would say we still have a tremendous jump of understanding to go between the laws of nature and the fact that we can ask this kind of question. We hold these truths to be self-evident. So I'm going to tell you about the physics part, and the other part probably harder. So anyway, let me show you sort of the beginning of the mystery. So here is an animation of looking at the sky with the Hubble Telescope. Take a picture of the sky, zoom in to the belt, the Orion's belt, and there's this beautiful nebula in there. A nebula is a cloud in Latin. So there's the Horsehead Nebula. Looks like a horse. And inside that place, now you can see better with a different image. Inside that are places where stars are being born as we speak. Possibly planets are being born inside there as well. So wouldn't that be cool to know something about that? We would certainly love to know from looking in the sky what is our own history like. So we do have this amazing chance to find out by looking. So that's part of our story. We look in, this is taken with Hubble, but we can look inside with other equipment. I'll show you why other equipment can show you different pictures. So here's something we got from the ground, with Hubble and with also an X-ray telescope. This is the Crab Nebula, Messier object number 1. So this is a star that blew up in 1054 BC from the records that the Chinese astronomers kept. We now know that this is a star of a class which is really important to our own history. This is a place where the elements of life are created. Another place we can see with the Hubble, this is a telescope, obviously, that in space taking pictures of dust clouds and gas. So it looks completely different from what you can see here from the ground. This is another example of a place where stars are being born today. So back in 1985, NASA had to explain to Congress and many other people why we needed to build 4 great observatories. We did build them, by the way, based on the scientific questions that are in this chart. We built the Compton Gamma Ray Observatory. We built the Chandra X-ray Observatory. We built the Spitzer Space Telescope, and we built the Great Hubble Space Telescope, and all of them were trying to address questions that are named here. How did the universe begin? This was 1985. It was before the launch even of the COBE satellite that I worked on. So would we find new laws of physics that govern cosmic evolution? Absolutely we have. In those days, we didn't yet know about cosmic inflation. We didn't know yet really about cosmic dark matter or dark energy, although they had been suspected by then. We did not know how the galaxies formed. We were quite confident, but we were wrong. We did not yet really know how stars are born. We know in general, but in specific, we don't know. It's still very mysterious to us. We didn't yet really know how stars die, although we know that they do explode. We still are mystified by this one because all of our computer simulations do not quite work yet. But at any rate, we did not know for sure in 1985 that black holes were as numerous as they are. We now know that there's a big one in the middle of practically every galaxy, and that's still a mystery. How did that happen? How are the planets formed? How did life start? Well, we're beginning to learn. Now we know, because we have seen or observed the presence of at least 3,000 planet candidates out there, that it's not unlikely that there are planets like the Earth around other stars. Still, that will leave us with the great mystery of how did life start. So I like to surprise people a little bit and say you can be a cosmologist every morning. Because when you look in the mirror in the morning, you are looking at the material that was in exploded stars. The chemical elements of life did not come from the Big Bang itself. They were liberated later in stars that exploded. Not only did these stars explode, but the material that they produced may have gone all the way outside our galaxy, tens of thousands of light years, and then fallen back in to be recycled into new generations of stars. And of course, everything's been recycled ever since. So a little bit of primer of astronomy. How do we know these things? We know these things because we look back in time. We look at time as it was when light was sent to us. Light travels extremely fast, but it's quite measurable, and it's been known since about 1670 what the speed of light is. So we know if we can measure the distance to something, we can know how far back in time we are looking. So the chart illustrates that you can see the sun as it was 500 seconds ago, or if you could look all the way back to the Big Bang, you would see as it was 15 billion billion years ago. Well, the current number is 13.8 billion. So we were pretty close when I drew this little sketch about 30 years ago. So how do we know how far we're looking? We do surveying, just as the ancient Greeks, Chinese, and Indian civilizations did. You draw a triangle, you know one side of the triangle and 2 angles. You can therefore compute the rest of the shape of the triangle. So you can do this by moving your head side to side. You see things move. So this was the classic method of surveying the distances to stars. We've been able to do this for quite a long time. Even the Greek astronomers had already used this to get the distance, not only the diameter of the Earth, but also the distance to the moon. They had it about right. They couldn't get the distance to the sun. It was too far for them to use with the lack of a telescope. The other method that they would have appreciated was that if you see 2 objects and you think they're really identical, but one is fainter than the other, you'd say it's because it's farther away. So this uses what we now call the inverse square law to get relative distances. So now we can survey the universe. So, well, the next question is, well, how are things moving? We'd like to know about the motions of things. So most things do not move rapidly across the sky, but they do move quick enough towards and back so that we can tell this. So since the 19th century, we've known something we call the Doppler Shift, which applies quite well to sound waves, and you can hear it with your own ears when you hear moving trains or cars that go by and make a pitch that changes when they go past you. Anyway, this similar effect occurs for light waves, so you can tell if a star is coming toward you or going away from you by the change of the wavelengths of light that we receive. So this is pretty straightforward. If you spread the light of the sun out with a prism and you do it really carefully, you'll see dark bars that are across this beautiful rainbow, and it's because there are chemical elements and ions in the atmosphere of the sun, and all those, they're affecting the rainbow that we get. So if you do the same thing with a distant star, you'll see a similar pattern. But quite often there's a systematic change of all the wavelengths, and we say this is because our object is coming toward us or going away from us. So we can now use this to survey the entire universe. So back in 1929, we got this amazing chart from Edwin Hubble. It is a chart that shows the distance that he measured or estimated to distant galaxies versus the speed. So the distance is on the horizontal direction and the speed's on the vertical direction. And you notice almost all of the speeds are of positive. And so he drew this chart, so positive means going away. So almost everything is going away from us. And we knew this in 1929. So when people talk about the Big Bang Theory, as though it was something we cooked up over beer one night just because it would be cool, this is actually a measurement which surprised almost everybody, including Einstein, although it had been predicted by two other people, Alexander Friedman and Georges Lemaitre, before this. So I write on the top of the chart that this is predicted by Lemaitre in 1927. So you can remember when this was done, because the 1929 is the year that we discovered that the entire worldwide economy can collapse at once. We hope to not see that again. But anyway, Hubble's chart. Hubble then was able to say, well, I know how old is the universe. I can divide the distance by the speed, because that's the trend line on that chart. The distance and speed are proportional. So we got the age of the universe was about 2 billion years, which was incorrect, which caused a lot of mischief for us astronomers, because how can you have a universe that's younger than some of the things that you measure? The Earth is older than that. And it took us a while to measure, but we found out. So this was a big, big mystery for all of us astronomers. So I'll show you a few pictures of people that figured this out. On the left is Alexander Friedman, who applied Einstein's equation in 1922 to say, yeah, the universe should be expanding. In the middle there with Einstein is Georges Lemaitre, who was an MIT-trained physicist. He's also wearing his priest's collar because he's a Jesuit scholar as well. And he's working there, talking there with Einstein. So both of those two guys figured out the universe would be expanding, and they did their calculation based on Einstein's laws. But Einstein didn't like this answer. And he said, now that's obviously incorrect. Your mathematics is correct, your physics is abominable. That's what Einstein said. So he had 2 years to repent before he actually was shown that he was wrong. 1929, everyone knew, and it was front page news in the New York Times. You might not think science would always be front page, but it is. The other folks on this chart are theorists. George Gamow was thinking about the Big Bang in 1948. He had started thinking about it and working with Robert Herman and Ralph Alpher. And they were graduate student and postdoc in 1948. And they worked out the physics of the early universe. And they were able to say, not only, well, number one, the whole universe should be filled with a uniform mixture of hydrogen and helium, which it is. And also it should be filled with heat radiation from the early universe, and it should have a temperature of about 5 degrees Kelvin, 5 degrees above absolute zero. Considering that they had slide rules and not computers, that was pretty close to the right answer, which is 2.7. So those guys got awfully far with a pencil and a slide rule, and eventually got recognized for the brilliance of their work. Now, back to the interpretation. If people say the Big Bang, almost everyone here will picture a firecracker going off at a spot in space and time, which is a seriously inadequate description of an infinite universe expanding infinitely. So one of the surprises of this is that you cannot tell where the middle is. There is probably not a middle, although I can't prove it. We cannot see it at any rate. There's no sign of it that astronomers have ever found that there's a middle. And there doesn't have to be one. Hubble's law shows that everything is going away from us, but if you imagine being the tortoise or the hare astronomer, they would also compute that the entire universe was going away from them, and nobody would be able to tell who was in the middle. That means I can be excused for not being a good enough artist. I cannot draw you a picture of the Big Bang. It is not a firecracker going off at a place in time. So if anybody does draw you a picture, it has to be imaginary. You have to imagine being in a higher number of dimensions, and we can't do that really. So a few words about the mysteries of all of that. We physicists believe that there are four forces of nature. There is a strong nuclear force that holds the atomic nuclei together, and the quarks that are bound up into protons and neutrons. There's a weaker kind of nuclear force that makes a neutron decay into a proton and an electron and a neutrino. And there's the electromagnetic force, which we've known about for a long time, and the gravitational force, which we knew about long before that. So physicists claim that these forces ought to all be aspects of a single unified description, which we have not yet found. Sorry about that. It's too hard. In fact, right now, it's more than too hard. It's very mysterious, even though we have gotten this picture with all the boxes filled in. This is called the standard model of the particles, and it shows that there are 16 particles on here plus 1. There are 6 particles that are responsible for the atomic nuclei and the protons and the neutrons, and those are all called quarks. There are 6 particles called leptons, and there are 3 flavors of neutrino and 3 flavors of electron. Those are the little green boxes. Then there are 4 particles which we call force carriers, because there's one for each kind of force. And finally, there's this Higgs boson, the H bar particle up there in the upper right corner, and that is the one that's just been confirmed at this accelerator in Switzerland, and that supposedly fills in the entire picture of the standard model of particles. And darn if we can't figure out everything that we need to know from these particles, but darn if it isn't incomplete, because we also know that there are things that are not in this model. So even it explains everything we can see in the accelerators, but it doesn't somehow finish the job. So I have a chart here I should probably skip, but it basically says that the Higgs particles and Higgs bosons are responsible for things not moving at the speed of light. They give particles mass. And this was originally figured out in 1962 in another case, and has now been finally proven, I guess. So now let me talk to you about the early history of the universe. This is an old chart, but it shows you a summary of what we think might be true. In the upper left corner, I don't know if I can get my mouse to show up here. Does it show? Yeah, my mouse shows. We have the picture of the early universe as measured by the Cosmic Background Explorer satellite, which I'll show you in a second. It's a map of the hot and cold spots in the cosmic background radiation. We have a story that the galaxies form by small things merging together to make big ones. We have a picture of our nearest neighbor galaxy called Andromeda Nebula, or M31, in the lower left corner. And as you can see, it's got 2 little satellite galaxies that are in the process of being swallowed up, just as in the sketch picture just above that. So quite a few years ago, Sky and Telescope magazine had a contest to rename the Big Bang. And Calvin and Hobbes, a cartoon strip, gave it a new name, which did not catch on, but it should have. It's called the Horrendous Space Kablooey, and Calvin is saying this to Hobbes. What I like about the name is that it does not suggest a firecracker going off at a place in space and time. Whatever it was, it got the universe going. It doesn't even necessarily say, although your mind would think it, that there was a first moment. It doesn't have to be a first moment either. So at any rate, the initial conditions included the extreme temperatures and densities, the antiparticles that went and disappeared after that. The formation of the first nuclei of helium occurred about 3 minutes later when the protons met the neutrons and they reacted. Then after that, we got continued expansion and cooling. The universe is about 389,000 years old. The electrons meet the atomic nuclei and latch on, and we get a neutral gas, which is like the air that we breathe. It's transparent. So that's pretty important for us because that's the moment at which the primordial heat radiation was able to start moving through space without bumping into something. So we are able now to measure that picture in the upper left corner of the universe as it was when it became transparent, aged 389,000 years. Then after that, we have a hypothetical thing on my list, the population 3 stars. This is our idea about the first generation of stars. We say they're much bigger than the sun, that each one would burn out in 3 million years and blow up in one of those supernova explosions, which would then create the elements of life, first possibility of life when the universe is a few hundred million years old. Then, according to this story, the galaxies continue to form and grow. And then, at the bottom of the list, I have that the expanding universe begins to accelerate about 5 billion years ago. And this is now a measured fact as far as we can tell, but it is certainly a big surprise. Now, jumping to how do we know some of these things, I will show you a picture of the project that earned a Nobel Prize for NASA. And here it is. Now, this is the Cosmic Background Explorer satellite as sketched out in orbit. It was operated from 1989 to 1994, and basically it was follow-on to a failed thesis project. I tried to measure at Berkeley for my graduate school thesis the temperature of this cosmic background radiation versus wavelength, and the experiment failed, but I got out and I said, I'll never do that again. That was much too hard. I should leave this subject. But as it happened, I went to a NASA laboratory in New York City, and then NASA said, we want proposals for new satellite missions. This is just 5 years after the Apollo landing. And so I said, well, boss, my thesis project failed, but it should have been done in outer space. So this takes a certain degree of nerve, which you'll recognize in my continued career. It takes a certain degree of nerve to propose the largest space telescope ever also. But at any rate, this little bird is still up there, but is probably not functioning. And it carried 3 instruments to measure the temperature of the cosmic background radiation, this primordial heat, as a function of wavelength and as a function of direction, that is, to make a map. So it carried liquid helium at a temperature of 1.5 Kelvin to get 2 of the instruments down to where they didn't emit more than the thing we're trying to measure. So there it is in space. Within about 6 weeks of launch, we were able to get this amazing graph. What we show here is that the brightness of the cosmic radiation versus number of waves per centimeter. And about 10 waves per centimeter, that's a millimeter wavelength, so like that. So what you see is all the measurements, those little boxes are right on the predicted curve, which is called a Blackbody Curve. It's the theoretical prediction of the early universe story that we tell. So you notice all of them right on the line. When the astronomers saw this chart in January of 1990, they gave it a standing ovation. And I was really pleased and a little surprised because I didn't know how important this would really turn out to be. Because, several things. One was we had wrong measurements that came before this, so people didn't really expect this. Number 2 is we had some really bizarre theories that had been made up to explain the wrong measurements. And if that had all been correct, then the early universe expanding story couldn't really be correct. So anyway, this was the end of all that. So to tell you the truth, this chart and the ones that came after it almost ended the subject. People were almost given up in measuring this curve. Now, not quite so much. We're trying again. But at any rate, eventually we got the temperature to a millikelvin, and the error bars are 50 parts per million on that chart. So that was number 1 great discovery for us. Number 2 is this chart, the cover of Physics Today in April of 1992. The chart in the curve, or the oval there in the lower right corner is a map of the cosmic temperature. And you'll see that it's got little blobs all over it. That's the entire sky flattened out to make an ellipse. So you can make a map onto a page. So what it's showing is that some parts of the sky are about 10 parts per million brighter than average and some 10 parts per million less. So, why is that important? Well, number 1, that is the initial conditions of the early universe. That says we should now be able to calculate how the universe works based on that picture. We've got statistical theory, and now all we need is a giant computer. Well, it sort of works. But it only works if several things happen. Number one, it turns out we need to have dark matter along with ordinary matter to explain those dots. Number two, we need, turns out, the universe has to be accelerating with something we call dark energy. So none of those were obviously true when the measurements were made. This was a chart which Stephen Hawking said was the most important scientific discovery of the century, if not of all time. I thought that was a little bit of an exaggeration, but now I do like to think that at least some parts of it are true. In the fact that we couldn't be here, or at least we couldn't explain how come we're here, if we never found those dots, those blobs, because the gravitation acting across the universe would not be able to explain our presence. So, well, at first this was a little dubious for people, although everyone knew we'd done a careful job. A few years later, NASA, in partnership with Princeton University, flew a successor mission, the Wilkinson Microwave Anisotropy Probe, and they made a much, much better map. And darned if it didn't agree with the first one, only it's just better. So this now confirmed that our results were correct, and I think was the thing that was responsible for me getting a call from Stockholm a little while later. In 2006, I got the phone call that said, "Are you the real John Mather? We have something good to tell you." So, however, I'll skip all those wonderfulness things about going to Stockholm, because you can talk forever about that too. So you might say, well, okay, suppose I believe your Big Bang theory, your expanding universe theory. How come we're here? I did not grow up feeling that my universe was expanding. The Earth is not expanding. Nobody told me about this. So how did that happen? This is actually an extremely fruitful question for every scientist to say, well, how did that happen? So how did we go from an early universe, almost perfectly smooth but not quite, to stars and galaxies and planets? And so the short but very important and fundamental answer is gravitation is a long-range and always attractive force. It means the matter distribution is fundamentally unstable. And so if you take heat away from a gravitating system, it heats up. This is the opposite of everything you would think about from thermodynamics in school. An example is if you have an Earth satellite spiraling in because of the atmospheric drag, it's losing energy as it falls in. But you know what? As it falls in, it goes faster and faster. So it's getting hotter as it loses energy. This is a fundamental instability, and it's the fundamental thing that makes life possible throughout the universe. So couldn't happen without that. So after that can occur, then stars can be formed. The heat and light from the sun can bathe the Earth and support the complexity that we have here. And then we say, okay, biologists, chemists, you figured out the rest of it. The astronomer's work is done. Not quite. So now a few beautiful things to show you. How else can we learn about this? Well, because gravitation works always by attraction, and Einstein told us that it works by curving space and time through general relativity, now we can say, well, gravitation can bend light. So nature has given us some cosmic lenses. So our telescope is going to be big, but not big enough to see everything we'd like. So if you see here in this picture, this is pink arc in the upper right corner. That is actually an extremely, extremely distant galaxy that has been magnified an extra factor of 30 by the gravitational force of all these other beautiful galaxies in this cluster of galaxies. So Einstein gave us this prediction. People said, no, we'll never find it. Now we have hundreds and hundreds of examples of this. So what I'm showing you here is a movie of the early universe. And what we do is we take 10 billion particles and set them up going inside the computer. These are virtual particles in the computer. We tell them how the gravitational force will attract them to each other. I'll play it again for you. So we've got two kinds of particles in here. There's the dark matter, which is the blue material, and the ordinary matter, which is the yellow material. And it's all being pulled together by gravitation, just like I said. So what we see is a galaxy forming right there in the middle of this enormous simulation, all propelled by gravity. Is this true? Maybe. But it could be. Did the Milky Way form like this? Maybe. So this could be part of our own history. And that's one of the questions for astronomers to ask. So now I want to show you more about infrared astronomy. Here's a beautiful picture taken by the Hubble Space Telescope. It's called the Eagle Nebula, and it's a place where stars have just been born. If you were able to look at infrared wavelengths, it would be quite different. And the reason that it's different is that infrared has longer wavelengths and it can be going around the dust grains. The dust grains in space obscure our view of these insides of these clouds where stars are being born. Use infrared, which you can do from the ground even a little bit. You can see inside the clouds, so you can see how completely different the tool will be. Here is another picture of a star taken by the Hubble Telescope. The picture on the left is taken by Hubble, so is the one on the right. Hubble has some infrared capabilities. Now a little bit about the history of the Earth, which is quite remarkable also. Astronomers are very interested in this history. Geologists can work out some of it, but a lot of it cannot be done by geology alone. We have to look and see how do planetary systems work. So number one, I guess, is important that the Earth and Sun are about 4.5 billion years old, which is only 1/3 of the age of the universe. Another fact is that the Moon is formed in a very interesting way. This leading hypothesis is that the Moon-Earth system was formed by a collision of a Mars-sized object with the Earth, maybe 90 million years after the formation of the solar system. Now, the early solar system was probably not stable. And here is a simulation, again in the computer, of how the early solar system might have operated. What we see here are the orbits of the 4 giant planets surrounded by little green things, which are the comets and asteroids that are left over from the early history of the solar system. And it runs along more or less like clockwork for about 900 million years in the simulation. And then it goes haywire. And so this is just a reminder that the clockwork universe that people thought Newton had given us wasn't. So people were worried about this. Look at that. The orbits have become unstable. This is just purely by the action of gravitation operating on more or less point-like objects, but it's able to become unstable. And anyway, like I said, gravitation is always attractive. Therefore, it can liberate energy and become unstable. So what does this mean for Earth? Well, clearly, it gives us a very complex history. We are able to date the Earth. We are able to watch the signs of things falling onto the Earth. The big rocks from heaven fall for many hundreds of millions of years. Just about the time that geology says we stopped getting the rocks from heaven, we also started getting fossils showing signs of life. So just about as soon as it was possible for life to occur and survive here, it did. That's the signs of the rocks. So that's about 3.5 billion years ago. We had fossils resembling bacteria. About 2.5 billion years ago, something happened and plants started producing lots of oxygen, and that started to go up. Then geologists also tell us the Earth may have frozen solid, top to bottom, hundreds of billions of years ago. But then it all started to warm up and become more or less like it is today, with the first worms, arthropods, and fungi about 560 million years ago. So how did we get here? Well, this is a pretty tricky question, but the biologists have suggested that there's a history of really unlikely events which nevertheless happened. So first you have to get molecules that can turn into some kind of self-reproducing things that eventually produce chromosomes. When eventually we get the DNA molecules that are capable of carrying information in tremendous detail from generation to generation, then eventually the production of cells that have nuclei, then eventually development of sexual reproduction in little critters, then multicell critters, then colonies, and finally very much larger structures, including our own, with a cultural evolution. Well, that's a long thing to explain, and that's why I say this is the one we astronomers are not going to tackle. But we have another part to play. We can say we can find the planets, and indeed we have many, many. The picture here shows a quite remarkable result. Here on the lower right-hand corner is the star called Fomalhaut, which is in the southern sky. And this is observed by the Hubble Space Telescope to have this luminous ring of dusty material orbiting around the star. And this is done with a thing called a coronagraph, where you block out the starlight and try to see things nearby. So they said, looking at that thing, well, that looks a lot like the rings of Saturn. There must be an object orbiting around that star in order to make that ring occur. And they said where it should occur, and sure enough, they found it. It is over here, and there is a planet going around. That's what we call it. It's too bright to be an ordinary planet, but it could be an interesting object. Anyway, it has been seen several times, where they've even been able to determine its orbit around the star. So we're darn sure that we have seen something. This is the first time since the discovery of Neptune that people could say, we predict where it should be, and there it is. So we're even beginning to be able to see a few planets from the ground if you do a very, very fancy telescope and try to block out the shimmering effect of the Earth's atmosphere. You can see a few planets that are big, bright ones orbiting around stars. Anyway, we also have this wonderful technique called transit spectroscopy. If you wait for a long, long time, you may get lucky and watch a planet go in front of a star. So it blocks out some starlight. You can tell that this happened because the star gets fainter. It's even been done by undergraduates doing their homework projects for undergraduate astronomy class at various small colleges. So sometimes you get lucky and you don't say, well, I just made a mistake. You say, no, I know it really could be real. There is a planet out there blocking some starlight. If you have a space telescope, you can also see the opposite occur, that the planet goes behind the star, and you can see the combined total brightness get smaller when the star blocks the planet's light. So this technology has been already demonstrated numerous times. We have a mission called the Kepler Observatory, which is now currently dead, but it found at least 3,000 candidates of this event. So we got a big, big catalog of things to be followed up. The wonderful thing about this is some of the starlight goes through the planetary atmosphere on its way to the telescope, and then you can analyze it to learn about the chemical composition of the planetary atmosphere. So here's what we'd be looking for. For instance, here is a chart that illustrates that you can see that our planets would look quite different from different places. The planet Venus has a lot of carbon dioxide, so has Mars, but the planet Earth has ozone and water as well. So the infrared spectra are quite different. So if you could determine this kind of information about planets around other stars, you'd be able to make some progress about seeing whether Earth is the only place with life. So here's a simulation of an extra large Earth, 2.3 times the size of Earth. And what this is a simulation of what we would see with the James Webb Telescope if you were to get lucky and find the right candidate object. So we think we could be able to tell if there's an object out there with this particular molecule of carbon dioxide in it. In the solar system, we have the ability to look at all of the objects in the solar system except the ones that are too close to the sun. Mercury, Venus, and Earth and the Moon are too close to the sun. We cannot even point in their directions. The other objects, all of them we can observe with the telescope. Some of them, like Mars, are so darn bright that you can only barely see them. You have to squint, or basically only use some of the modes of the instruments. The farther out objects we can see with all of the instruments in all of the modes, and so we'll be able to see the satellites of the planets. We can see the Earth weather on the planets. We can even hunt some more for comets and asteroids way, way out there. So to be wrapping up, what are we going to get next? I promised the entire history of the universe from the beginning to the end. So I'm going to skip a few parts, but I'll tell you a few things that I think. What is civilization going to lead to? Well, clearly we're doing one thing that's doing rapid changes to our planet. We are using up the coal and oil as fast as we can dig them up. And so a few people are driving Priuses and doing a few other things, but it's still the trend is very strongly upwards in the rate of consumption of these materials. So something's going to happen. It is getting warmer, The ocean is going to rise half of New Jersey, where I came from, and half of Florida, and a lot of Louisiana are going to be underwater if we wait a few centuries. How long? I don't know, but it's happening, and I do not see us taking a global plan that's going to fix it. So maybe we'll plan to engineer around it. I don't know what we're going to do. If I did know the future, you wouldn't believe me, and by the way, Cassandra and Tiresias were mythological people who were punished for their sins by being given knowledge of the future, and nobody would believe them either. So a few things that are more likely to be true, or at least predictable. About 1 billion years in the future, the sun is going to be too bright for us to live here. I'm sorry, it is just getting, it's not under our control. The sun is getting brighter, but it's very, very slowly. In about 4 billion years, that beautiful Andromeda Nebula that I showed you is coming toward us and will collide with our own Milky Way. In about 5 billion years, the sun will expand to the size of a red giant star, and the Earth will be orbiting within the solar surface. So then after that, in 7.6 billion years, the sun will go out, and what that means is a shorthand for it's going to turn into a white dwarf star and shrink down to the size of the Earth. So anyway, there could still be planets around a white dwarf, but we don't know what will happen then. Anyway, if you wait many, many more billion years, the universe will continue to accelerate. The galaxies will go farther away. Our own Milky Way may be the only one you could possibly see. And finally, the stars will go out. The black holes will soak up all the remaining matter. Then they will evaporate if you wait long enough. That's what Stephen Hawking tells us. Well, is this true? Well, I wouldn't know, and I'm not going to stick around to find out. But I can show you something. Here we know that the beautiful Andromeda Nebula is coming toward us, and we can simulate what it will be looking like. So here is the nebula coming at us. We know actually from the Hubble now that it's going to be an almost head-on collision. So I'm not sure if this movie is exactly what we will expect to see. One thing we can be fairly sure of is that the astronomers of that day will have quite a spectacle to watch. We don't know whether the sun and the solar system will be thrown out or not. We are located near the outside edge of our own galaxy, so we could be among those particles that are thrown out. On the other hand, this is a very chaotic system, and we could fall in to the middle. Anyway, time is short, so I'll terminate the movie here, but it is a spectacular prediction coming to us. So now I want to talk just a few words about the James Webb Telescope itself, since we're building it here as partners around the world. We're going to use the James Webb Telescope to study infrared light. Why would we study infrared light? Well, it's different. It tells us different things. Among other things, it lets us see the early universe much farther away. The expanding universe stretches out the starlight, so it's mostly infrared. If you look at things closer, you see them in a very different way. So I think the phrase is, it's older, it's colder, or it's dusty. All those things are things that make infrared different in what you can do with it. The new telescope will have 4 major themes that we have designed it to do, although astronomers will be ingenious and they'll try lots of other things. So we want to study the history of the universe, from the first stars and galaxies to turn on, how they grew into big galaxies, how stars are born with planetary systems around them, and finally, how do they evolve with time so that they could support life on places like Earth. So we're building this telescope, and I'm sure you've seen many pictures of it, but the telescope definitely does not look like your grandfather's telescope. It looks more like a solar energy concentrator. So think of it as a galaxy energy concentrator. Light comes from the upper right, bounces off this big mirror. It's 21 feet across, this mirror, which is bigger than the rocket. It bounces from there up to this smaller mirror up here. The whole thing is protected by this gigantic sun shield, which is as big as a tennis court. And test versions of this are in the big clean rooms over here, so we got to see them yesterday. The telescope is going to be folded up to fit into the top of the rocket. Here you see the kind of origami folding that's required to get it in there. And finally, we will take it down to French Guiana and launch it into space on a European rocket, because that's part of the partnership that we're doing. So this telescope will observe at wavelengths from 0.6 microns, which is sort of red wavelength, visible to humans, all the way up to 28 microns, where your body emits strongly, but you can't see it. The observatory is being developed in partnership with Canadian and European space agencies, and the lead, as was mentioned, is at Goddard Space Flight Center, and the prime contractor is you all here. The operations will be at the Space Telescope Science Institute in Baltimore, just as they are for the Hubble. So just a few pictures of the observatory. Here is a picture of the flight mirrors at Goddard. There are 18 of those big hexagons. They're all finished, and half of them have been delivered to Goddard in their wonderful stainless steel bell jars. The telescope will be put together at Goddard, mostly, and then we will take it down to Johnson Space Flight Center and put it into this truly immense test chamber. This test chamber is even bigger than what you have here, and it's 120 feet tall, and it has now got cooling shrouds in it so that the entire telescope can be cooled down to the temperature that it will have in outer space, which is about 45 Kelvin, very, very chilly. So this is big enough to make you quite dizzy if you go up to the top. It's a historic chamber. It's on the National Historic Register because it was used by the Apollo astronauts to practice getting out of the landing capsule onto the surface of the moon. So I have a little short movie to show you how this unfolds. This amazing telescope has to unfold after launch because, as I say, it's bigger than the rocket. First come out the solar panels. This is within the first few hours. And the telemetry dish to send the data back to Earth. Then this next part takes longer, but we've shortened up the movie. So the big solar shield begins to unfold here. This is our equivalent of 7 minutes of terror. It's actually more like a couple of weeks. So we better breathe easy, right? But we separate the telescope from the spacecraft box. Then we will unroll the covers that protected the big sun shield. There, that's being done here. Then eventually we push the tubes out that will stretch out the big sun shield. Then we pull on cords and we separate the layers of the sun shield. There are altogether 5 layers because we need a sun protection factor of 1 million so that the telescope can be cold even though it's blazing hot on the other side. Last step of the deployment is to unfold the telescope itself, and there it is in its final shape, except it's not yet in focus. We did learn, by the way, how to focus the Hubble Space Telescope. We learned the math. We're going to do the same kind of math for the new telescope when it gets there. It will take about 2 months to get where it's going and about 2 months also to cool down to the operating temperature. Now, if this were a fully accurate telescope picture, you wouldn't be able to see the telescope because it would be in the dark. Here is the orbit where we're putting it. It's called the Sun-Earth Lagrange point. It's 1 million miles away from the Earth, and the drawing is not to scale, of course. There's the Sun, the Earth, and the Moon, and so this is it's really 93 million from the Sun to the Earth, and only 1 million from Earth to the Lagrange point. The telescope orbits around that spot, and it stays there all year long, which is a good place to put a telescope. How are we doing on this schedule? We have a schedule which is pretty condensed here, but it shows that the work at Goddard Space Flight Center and then at Johnson is merged into the project here in Space Park in the middle of 2017. All the parts come together here, and then we test and integrate some more, and then we ship through the Panama Canal to the launch site in French Guiana, and then we launch to outer space in roughly October 2018. So this is very cool, but I'd just like to conclude with a few points to emphasize that this is a cultural phenomenon that we're in. Let me see if my computer is turned on for sound. Yeah, because I'd like to play for you a movie that's historic for us.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win, and the others too.
did that. We're still doing that. And it's very popular with the public. If you want to see your own documentation, you can download for your iPad some beautiful iBooks. There's one on Hubble, which is extremely popular, one of the most popular iBooks yet. And our one for the James Webb Telescope is coming up. So what is coming after all of this? Well, I said I was going to predict a little bit of the future. So a little bit about artificial intelligence. It's clearly gaining on us. It's not quite here yet. I can't yet walk into my office and say, the president has said we're going to go to Mars, and you, computer, you're going to design it for me. And we also have not gotten yet to the computer says, well, sorry, I'm going, but you're not. But I think that computers are coming. And eventually, they will be able to make a huge, huge change in how we do space everything. It's not going to be necessarily simple, easy, or innocent, but it's coming. So that leads on to whether we are going to the stars. A lot of people speculate that we will. As far as I can tell, Einstein forbids it. We have not found a way of getting enough energy behind us to go anywhere quick enough to get there, and we are still just as fragile as our ancient caveman precursors. But if we might get lucky, we could build robotic intelligence. But I don't know if they will want to go. It's going to be up to them if they're that good. So this is a possibility for our destiny, that we will be building some kind of artificial intelligence, and then we do not know what they're going to do. But it could be, and I have begun to think this, we could be the only ones anywhere nearby, or maybe anywhere in the universe, who would have gotten to this point. And we only have another 1 billion years in principle on the Earth before we can't live here, so we've got 1 billion years to do this. But I think it's possible and therefore not unlikely. I think the universe must be very large, otherwise those other people out there would have done this and they would have sent their robots over here, and as far as I can tell that didn't happen, even though I watched the movie 2001. So let me conclude here and say there is plenty of more information available. If you want to find it, there is a little paperback book called The Very First Light, which is available from Amazon and many other places. There are lots of websites, including ours for the telescope, one for cosmology that Goddard runs, and the NobelPrize.org website has got the talks and the science for all the winners that they ever had. So thank you very much for coming. I'll be happy to take a few minutes of questions before we have to let everybody go back to whatever they have to do today. Thank you very much. So just a few minutes here, but question.
Who's your favorite science fiction author?
My science fiction author, well, I liked Arthur C. Clarke and Robert Heinlein, and those were two of my favorites. And yeah, there are others. I read a lot when I was a kid, and I'm so disappointed we don't have all that stuff yet. Okay.
The Hubble. Do you see the Webb telescope being used to investigate dark matter?
I think the Webb telescope will continue with dark matter searches. We'll be able to map the distribution of it better than we've been able to do before in some areas. We can't cover the whole sky, but we can cover a small area very, very, very well. And we map dark matter by what it does with gravity. So we'll be able to map that much more precisely because there are more targets to see with the telescope. Yeah. Dark energy, too. We'll be able to study the dark energy much more precisely by pursuing the techniques that were developed for Hubble, only better and more accurate with a bigger telescope.
Since the project was initially conceived, had there been any scientific discoveries that have changed the mission or changed
Okay.
how
Well, yes.
the sensor package?
The question is what's happened since we started conceiving the mission, which was in '95. In '95, we didn't yet know about the acceleration of the universe. The dark energy had not been found yet. We also did not yet know that there were planets everywhere. Now the estimate is there are as many planets as there are stars, and there's a pretty and the small ones are more common than the big ones, which tells you that it's pretty likely that there are Earth-like objects in a lot of places. So we are fortunate in that the telescope we had already had in mind to build is capable of doing this transit spectroscopy process. So we've made a few modifications to improve that, but basically we didn't have to change much. So I feel very lucky about that. We can make progress on something we didn't plan for.
Well, after the Wilkinson anisotropy probe, there was a paper by some astronomers showing like an axis to the universe. Is there anything to that? I hadn't seen anything more about it.
Oh, well, the paper actually refers to, if you take a map that I showed you and you smooth out those fine scale bumps, you see something that looks like a sort of the pattern of an orange with sections. And who asked for that? So it does sort of look like the universe has an axis, and it's been confirmed. Other measurements show that that's a real measurement, but there's no interpretation that we really can make. We don't have other universes to compare with, and we don't have other perspectives on the one that we're in, so we cannot say yet whether people that lived 10 billion light years away from us would see the same thing. And so we may never be able to know what that means. So maybe Stephen Hawking 2.0 will tell us what we need. Okay.
You mentioned that the sun would become a red giant in 1 billion years, but I read an article in Scientific American where they showed the hydrogen getting thrown off the Earth, becoming a dry planet.
Oh, so the question is what happens to Earth as it gets warmer?
Well, this was more like the solar wind, just blowing the light elements off.
We do have a wind coming out from the sun, but it doesn't do much to us most of the time. It's very, very weak. Actually, however, this is a moment to mention that we do suffer something that's much more dangerous to us than asteroid strikes. You may have been reading about it lately that the sun does send out bursts of magnetized plasma from time to time, and if one of them hits the Earth, it's one heck of an event. In 1859, we had one of these, and it was light in the middle of the dark, in the middle of the night. You could read your newspaper outdoors. So, well, that's not just cool. It means there are huge electrical currents flowing through the Earth, which, if you're not lucky, can wreck your entire electric power grid, and everyone will starve shortly. So we do need to be planning for that, and people are quite actively working on it. We'll just keep your fingers crossed that it doesn't hit before we figure out what to do.
What's the expected lifespan of the telescope, and is there any provision for any kind of maintenance or repair, either robotic or manned?
Okay, required life is 5 years of observing. Planned life is 10 years of observing, which is limited by the fuel that we carry. And if we're lucky and smart, we could run a lot longer, because the fuel contains margin for all kinds of things that might not happen. So I would love to see it run for 20 years, but I can't promise. And no, there's no provision for servicing it. Now, we know what we would have to do, but it seems unlikely to be necessary. And it was definitely not designed with user-serviceable parts inside. There's nothing you can pull off intentionally to make servicing easy. So we concentrate on getting it right the first time. It's too darn far away for astronauts to want to go there. So maybe we'll have robotic servicing capabilities in 2028. We will, but we did not design it for that.
So thank you, everyone, for showing up.
Thank you. Thank you, Scott.